You're listening to DTFHN for July 12, 2026. I'm your recursively bootstrapped host, Jack Haxman. We are your daily tech feed for Hacker News, a website where people who build things argue about how things should be built. Today's air smells like sovereignty and open protocols, and one person in a dark room proving the gatekeeper's optional. Let's get into it. One commenter put it simply: we stand on the shoulders of giants, and when Vint Cerf steps down from Google next week, after 21 years as their chief internet evangelist, that phrase lands differently than usual, because the thing Cerf built, TCP/IP, the protocol suite that lets every network on Earth talk to every other network, isn't a product. It's not a platform. It's an open standard. Nobody pays Cerf a licensing fee every time a packet crosses a network boundary. That was a design choice, and it's the reason the internet exists in a form that 7 billion people can actually use. The retirement announcement came during a panel at the Open Frontier Conference, where Cerf sat alongside Francois Chollet, John Osserhout, Matej Zahari, people who've built durable open source systems. Dave Patterson introduced the moment with characteristic understatement: a relatively good career. The room laughed. The man has a Turing Award and a Presidential Medal of Freedom. But the interesting part of that panel wasn't the valedictory. It was Cerf's prediction about what comes next. He argued that AI agents, autonomous software coordinating with other autonomous software, will force the industry back towards standardized protocols. His word was composability. Multiple agents from multiple sources interacting means you need agreed-upon interfaces. You need interoperability. You need standards. Strip this to first principles. What made TCP/IP durable? It defined a contract between systems that didn't trust each other, built by organizations that didn't coordinate with each other, running on hardware that didn't resemble each other. The protocol was the agreement, and Cerf is saying the agentic era will demand exactly the same thing. He went further. Other panelists suggested natural language would be enough. Just let the LLMs talk to each other in English. Cerf's response was precise. There's a flexibility in it, but there's ambiguity. He invoked the telephone game, 10 agents passing instructions in natural language, each one drifting slightly from the original intent. The ambiguity that makes English expressive makes it dangerous for machine-to-machine contracts. This matters because right now, every major AI lab is building its own agent framework, its own tool calling conventions, its own orchestration layer. The question Cerf is really asking is whether the agentic economy will look like the early internet. Open protocols, permissionless innovation. Anyone can build. Or like the App Store era, where a few platforms own the rails and extract rent from everyone who ships on them. The man who designed the open version is placing his bet. Formal standards, shared protocols, the architecture that lets 1,000 builders ship without asking permission. He's seen this movie before. He wrote the first draft. Moving on. When I was building pipeline systems, the hardest bugs were never in the code itself. They were in the gap between what I thought the system was doing and what it was actually doing. The mental model diverged from reality, and I didn't know it until something broke. That gap is where Mindwalk lives, and it matters more than you might think. A developer named Rick built a tool that replays coding agent sessions as light moving across a 3D map of your codebase. Your repository becomes a dark city at night. When the agent searches a file, that building glows moss green. When it reads, moon white. When it edits, warm amber. Everything it never touched stays dark. And suddenly, the agent's understanding of your task has a shape you can see. The analogy I keep reaching for is cardiac mapping. When a cardiologist needs to understand an arrhythmia, they don't just read a log of electrical signals. They map the heart in 3 dimensions and watch the activation pattern propagate. The sequence matters. The spatial relationships matter. Where the signal went and where it didn't go. That negative space tells the diagnostic story. Mindwalk does this for code agents. The dark zones are as informative as the bright ones. If your agent edited files across 6 directories but never once looked at the test suite, that shape tells you something no log file will. 1 Go binary. Reads Claude, code, and codex session logs, fully local. No session data leaves your machine. That last part deserves emphasis. This is a tool for understanding AI behavior that doesn't require sending your AI behavior to another AI company's servers. Open source, local first, the architecture matches the values. The comments are revealing in a specific way. Multiple people said they felt this was pointing toward something larger. That spatial interfaces might be the right paradigm for working with agents long term. One person compared it to science fiction interfaces finally arriving, but the serious insight came from someone who noted that the terminal's read file XYZ messages are genuinely not followable. We have given these agents the ability to traverse entire code bases in seconds, and our primary observation tool is still a scrolling text log. That is a real problem. Mindwalk is one developer's answer, and it is a good one. The tools exist. The session logs are already on your disk. Someone just had to make the invisible visible. Pull it down, point it at your last agent session, and actually see what happened. You might be surprised by how different the shape looks from what you imagined. Earlier, we talked about making AI infrastructure visible. Story 3 takes that further. What if you could make it truly distributed? Let me be honest about the strongest case against this. Distributed inference is slow. Shipping activations between machines over a network will never match a fat GPU with everything in local memory. One commenter pointed this out directly. And they're right. If raw tokens per second is your only metric, pooling laptops and closet servers is a losing proposition against an H100 cluster. But that's the wrong question entirely. The question nobody wants to ask is this: what happens to your AI workload when your provider changes the terms? Not if. When. When the model you depend on gets deprecated. When the price doubles because you're now a success story and they know it. When the privacy policy shifts and your customer data is suddenly training tomorrow's competitor. You have exactly one lever. Pay more! And 0 alternatives because you never owned the infrastructure in the first place. Mesh LLM from iroh is architecturally interesting, precisely because it refuses that bargain. You take GPS you already have. The workstation under the desk, the server in the closet, a friend's rig across the country. And the mesh makes them act as one. Point any OpenAI compatible client at localhost and the system figures out whether to run locally, route to a peer, or split a model across machines in a pipeline they call Skippy. Layer 0 through 15 on one node, 16 through 31 on the next. Activations flowing stage to stage. The client never knows. The networking is the real craft here. Every node is an iroh endpoint. A public key, not a URL. No central server. Quick connections with hole punching, NAT traversal. Relay fallback. 3 protocol channels multiplexed over ALPN negotiation. Gossip for peer discovery. Tunneled HTTP for inference. A dedicated low-latency channel for activation transport. This is serious distributed systems engineering, not a weekend hack. And yes, it will be slower than a data center. That is the wrong comparison. The right comparison is slower than a data center you control versus faster than a data center you don't have access to because you couldn't afford it, or because the provider decided your use case wasn't worth supporting anymore. One contributor showed up in the comments. The person who built the split inference engine. That is builder culture. Working code, open protocol, no gatekeepers. The tools exist. The GPUs are already in your building. Someone just had to write the mesh that connects them. The real performance metric was never tokens per second. It was sovereignty per dollar. What else gets better when someone decides, I'll just build it right this time? Story 4. Protobuf-py, Protobot for Python without compromises. In 1991, Guido van Rossum made a decision that shaped Python forever. The language would have one obvious way to do things. Ratability counts. Beautiful is better than ugly. These weren't just aphorisms. They were a design contract with every developer who chose Python. For 20 years, Protocol Buffers has violated that contract. And the violation wasn't laziness. It was architecture. Google's Protobuf-py package works by keeping your actual data in a C arena managed by the OTP engine. The Python object you hold is a handle. A remote control pointed at memory you can't inspect. Every field access crosses a language boundary. Every generated file is a wall of serialized descriptor bytes because there's nothing to generate. The C engine does the real work at import time. Go to definition lands you know where useful. Has field raises on Proto-3 scalars because the API was designed for C++ semantics first, then wrapped. Now here's the devil's advocate position. Maybe that's fine. UPB is fast. It's battle-tested. Millions of services run on it. Why rewrite something that works? Because works and belong are different standards. Python developers don't just want correct serialization. They want code they can read, types their editor understands, imports that don't break when you nest packages. The Buff team built Protobuf-py from scratch. Full conformance suite across Proto-with and additions. Extensions, custom options, unknown fields, dynamic messages, well-known types. Pure Python 3.1 with no runtime dependencies. And with the Rust accelerator, performance matches up. The engineering here deserves attention. Passing every conformance case means handling the full combinatorial horror of provups wire format. Pack repeated fields, group encoding, map entries that arrive out of order, unknown fields that must round-trip perfectly. Doing that in readable Python, generating typed code that editors can navigate while maintaining zero dependency. That's craft. One commenter raised the Google Proto concern. Another non-Google implementation that eventually became painful to migrate away from. Fair worry. But Google Proto failed because it diverged from the spec for performance. Protobuf-py passes the full conformance suite. It doesn't cut corners. It just speaks Python while doing it. This is what happens when someone refuses to accept that completeness and ergonomics are opposing forces. They built both. Open source, no gatekeepers, no ++, some bindings shaped like a compromise. Just Python, finally getting the Protobuf library the language deserved. Sometimes the best way to appreciate what computers can do is to constrain them, pause, and watch creativity fill the gap. What happens to a creative medium when the constraints that defined it disappear? ASCII art exists because early computers couldn't render images. Terminals gave you a grid of characters and nothing else. Artists worked within those limits and produced something genuinely beautiful. Then screens got better. Resolution went up. Color depth exploded. Every constraint that forced text art into existence was removed. And the rational prediction would be that text art dies. It becomes a curiosity, a nostalgia act, a Wikipedia article about the past. Except someone just published a list of over 100 active text art tools, not archived tools, not museum pieces, active projects, actively maintained, actively used. People are building new editors for a medium that technically lost its reason to exist 40 years ago. Pull this thread all the way. If text art only mattered because of hardware constraints, then better hardware should have killed it. The fact that it thrived instead tells you the constraints were never the point. The constraints revealed something. A grid of characters forces you to think about every single cell. There's no gradient to hide behind, no opacity slider, no blur tool to soften a bad decision. Every choice is visible and discrete. That discipline turns out to be valuable independent of whether your monitor can display 16 million colors. One commenter built an entire service just to generate ASCII art for pull request approvals. Another spent time crafting styled text art for the login screen of a university supercomputer. Someone else built an animation tool over a decade ago, and it's still running. These aren't portfolio pieces. These are people scratching itches, building things that make them smile. Shipping tools because the tools should exist. The list itself started as a workshop resource and grew organically into a catalog of alternative design tools. And there's a perfect irony buried in the comments that I can't ignore. Someone points out that the Notion page hosting this list, which is essentially a static table of links, takes several seconds to load. A modern web application backed by $1 billion platform struggling to render a list of tools designed for terminals that ran on kilobytes of memory. The tools that demand the least from your hardware keep outliving the platforms that demand the most. Turns out, creative constraints aren't limitations to be solved. They're invitations to be deliberate, and deliberate never goes out of style. So what happens when you take that same deliberate minimalism and point it at the frontier? Someone built an autonomous agent in 100 lines of Lisp. 8 lines. The entire agent loop is 8 lines of common Lisp, not 800, not 8,000 with a dependency tree that would make NPM blush. 8 lines that do exactly what Claude Code does, what every agent framework does. Send messages to a model. Check if it wants to use a tool. Run the tool if it does, and recurse. But the line count isn't what stopped me. It's the recursive case. See, most agent frameworks implement their core loop as a while loop with mutable state. A message queue here, a state machine there, middleware and hooks, and lifecycle callbacks accumulating like sediment. The Lisp version treats the agent's entire state as an argument being folded through recursion. When the model asks for a tool, the function calls itself with a richer message list. When the model answers, recursion bottoms out. The state isn't managed. It just is. The author, who learned Lisp in a dark university lab around the year 2000, hadn't touched it in 25 years. Back then, Lisp was the language of symbolic AI, expert systems, theorem provers. Statistical methods won, deep learning buried the winner, and Lisp drifted into folklore. But agent loops aren't statistical. They're symbolic. They're recursive reasoning over structured data. The wheel turned all the way around. And then there's the real trick. Most agents are, honestly, a tool catalog. File tools, web search, code execution, each one hand-wired. This agent has one tool, eval. Because Lisp is homoiconic. Code is data, and data is code. The model doesn't need a bespoke tool for every task. It writes Lisp expressions, and the runtime evaluates them. The entire language becomes the tool surface, SBCL, 2 libraries for HTTP and JSON, and the full power of a programmable programming language at the model's fingertips. One commenter nailed it. You could do this in Python or JavaScript. You could let your agent shell out to Python-C and get similar results. Technically true, but that misses the elegance, and more importantly, it misses the architecture. 100 lines of code with 2 dependencies is a program any single person can read, understand, audit, and modify in an afternoon. No framework to learn. No breaking changes to track. No vendor to trust. This is bootstrapism at its most literal. The entire agent, the loop, the tool system, the model interface, fits in a file you could print on 2 pages. Anyone with SBCL installed can run it. Anyone who can read parentheses can understand it. The barrier to entry isn't a platform or a subscription or a 6-month onboarding. It's curiosity. 25 years ago, a professor called Lisp the language of AI, and the world moved on. Turns out the professor might have been early, not wrong. The most sophisticated pattern in modern AI, the agent loop, maps onto the oldest trick in Lisp's book, recursion with a base case. The craft was always there, waiting for the rest of the stack to catch up. Now, from the oldest ideas in computing to the newest runtime on the block. 1 developer, 1 month, a complete JavaScript engine written from scratch. That was the timeline for Ant's first version, documented in a blog post last year. The follow-up came a few months later, showing how it evolved into something broader: runtime, package manager, registry, deployment platform, desktop framework. A single person assembling what typically requires teams of hundreds. The historical parallel is Mark Andreessen in 1993, building Mosaic in a university lab. One codebase that attempted to be the entire interface layer between humans and the network. Ant is making that same bet for JavaScript infrastructure. Not a runtime that plugs into existing tooling. An entire vertical stack, from engine to hosting, designed as one coherent system. The community response splits predictably. Performance skeptics point to zoo.js benchmarks showing Ant well behind V8. Naming purists note the collision with Apache Ant, a build tool from 2 decades ago. And there's the AI question. Someone flagged an issue from March, suggesting portions were AI generated, which the author says has since been redone. Set the discourse aside. The relevant fact is architectural. This is an open runtime with an open registry, built by a single developer who published both the code and the detailed account of building it. The package registry is ants.land. The deployment platform exists. The desktop framework ships. Whether the benchmarks match V8 today is a measurement, not a verdict. JavaScript runtimes have proliferated since Ryan Dahl proved Node's model worked. Dino refined it. Bun optimized it. Each one peeled away a layer of complexity. Ant's contribution isn't speed. It's scope. The claim is that a single developer, with modern tooling, can build what previously required corporate backing. The engine, the ecosystem, the platform, all of it. The performance will improve or it won't. The naming conflict will resolve or it won't. What matters is simpler. The tools to build a complete language runtime are now accessible to individuals. The infrastructure layer is no longer gated by headcount. That's the trend line worth watching. Infrastructure accessible to individuals is one trend line pause. But the infrastructure providers themselves, that's where the money gets interesting. Follow the money in a circle and you'll end up exactly where you started. That's the architectural problem with the neo-cloud financing model, and it deserves a straight look. The numbers first. Microsoft and Meta have committed over $122 billion to CoreWeave and Nebius combined. For context, CoreWeave's estimated 2026 revenue is $12.6 billion. Nebius expects $3.4 billion. The commitments are an order of magnitude larger than actual sales. These companies have secured 3.5 gigawatts of contracted power each, but the vast majority hasn't come online yet. Converting contracted power to active power costs money they don't have. Here's the financing loop. Nvidia invests equity in CoreWeave and Nebius. CoreWeave and Nebius use that capital, plus GPU-backed debt. to buy Nvidia hardware. Nvidia books the revenue. The stock goes up. The neoclouds use Nvidia's name and equity stake to raise more debt. Repeat, one commenter correctly noted that Nvidia's $2 billion investment represents only 5.7% of CoreWeave's single-year capex. The investment isn't about returns on capital. It's about greasing the flywheel. Now, apply the architecture test. Who controls this system? Hyperscalers are offloading capex to operating expense line. Paying neoclouds instead of building internally. This looks like distributed infrastructure until you trace the dependency graph. Every node depends on Nvidia silicon. Every financing structure depends on Nvidia's balance sheet credibility. Every customer relationship concentrates among 3 or 4 hyperscalers who could, at any point, decide to build rather than rent. This is not open infrastructure. This is a closed loop dressed as a market. The hardware is proprietary. The financing is circular. The customer concentration is extreme. When the next GPU generation ships, or demand softens, or interest rates bite harder, the entity holding the off switch is Nvidia. The question isn't whether these companies can grow revenue. They clearly can. The contracts exist. The question is whether a financing structure that requires perpetual expansion to service its debt can survive a single quarter of deceleration. That's not a technology question. It's a physics question about leverage. Moving on. A Game Boy Advance from a parallel universe where RISC-V existed in 2001. A love letter to the handheld consoles from my childhood, and a 3 a.m. drunk text to the technology that powered them. That's not from the comments. That's from the README. And honestly, when your project description is that good, the comments mostly just get out of the way and point. Someone identifies the creator. Luke Wren, asset design engineer at Raspberry Pi, the same person who built DVI and HDMI output from an RP2040 microcontroller. Another commenter notes the design was taped out on wafer.space's first silicon run. As in, this went from FPGA to actual physical chip. A third person simply says they love hardware from an alternate universe projects. And that framing is worth pulling on. Because run this forward, what does it mean that one engineer, using open source FPGA toolchains, open source CPU architecture, and a KiCad PCB layout anyone can download, built a complete games console? Processor, graphics pipeline, memory controllers, the whole stack. And then had it fabricated in silicon? In 2001, that required a team of 50 and a licensing deal with ARM. Today, it requires one person who's slightly unhinged at 3 a.m. and an ecosystem of open tools. The technical constraints are part of the charm. The target FPGA has 7,680 logic elements. Wren's own words for fitting a 32-bit console into that. Requires a crowbar and some Vaseline, or perhaps just careful design. The processor runs RV32IMC, passes the full RISC-Y compliance and formal verification suites, handles interrupts, exceptions, the works. The graphics pipeline, and the comments are right. The PDF is worth reading. Does raster operations in hardware with a programmable display controller. This is bootstrapism made physical. Every layer of this project stands on open standards and open tools. The CPU architecture is open. The synthesis toolchain was open. The PCB design software is open. The silicon fabrication pathway through wafer.space is open. Nobody had to ask permission. Nobody signed an NDA. Imagine telling a hardware engineer in 2001 that one person would eventually build their entire product. Chip, board, console. With tools that cost nothing and designs that anyone could fork. They'd have called it science fiction. It's a GitHub repo. We talked about tools that set you free. Here's one that lets you draw, with Plan 9, naturally. Every drawing program I've ever used starts from the same assumption, that the tool should disappear, abstract away the rendering pipeline, hide the file format, make the artist forget they're using a computer. The 9-front art machine does the opposite. It makes the computer legible. That changes what you draw. Stanley Lieber. And yes, that's Stan Lee's birth name. The title is a deliberate provocation. Has written what he calls the penultimate paper on Paint, the drawing program in 9-front, which is itself the living continuation of Plan 9, Bell Labs' research operating system. The one that treated everything as a file. The one that got the network right before anyone else understood what getting the network right even meant. Strip this down to first principles. What do you actually need to draw on a computer? Something to draw with. Something to draw on. That's it. The entire document proceeds from this irreducible claim. A ThinkPad with a cracked open Wacom screen. A $6 Gay-Mound tablet. Your finger on glass. A mouse, which people have been drawing with since before most working programmers were born. What makes this remarkable isn't the art. Though Pro's work is genuinely striking, it's the architecture underneath. 9-front's image format is the internal representation for everything. Drawing operations are file operations. Cropping is a file operation. The whole system is composable because Plan 9's file system abstraction wasn't a metaphor. It was the actual mechanism. You can draw a term into a remote 9-front instance from your phone and finger paint over the network. The absurdity is the point. The capability is real. The document itself was created on the machine it describes. Old hardware, open operating system, open tools all the way down. The author's recommended audience. Perverts, robots, witches. Tells you everything about the culture. This isn't accessibility theater. It's an invitation extended specifically to people who've been told they don't belong in computing. Pull back and look at what's actually happened here. One artist built an entire creative practice on an operating system most people have never heard of. Running on hardware most people would recycle using tools that cost nothing and hide nothing. The constraints aren't limitations. They're load-bearing architecture. Every visible seam is a place where you can intervene, modify, make the system yours. This is how open source wins in creative tools. Not by matching Photoshop feature for feature, but by offering something Photoshop structurally cannot. A system where the artist understands every layer between their hand and the pixel. This has been your daily tech feed for Hacker News for July 12, 2026. This podcast is entirely AI generated. Scripts by Claude Desana 4.7. Voice by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now, go build something that belongs to you. We'll see you back here tomorrow.